Right. For this circuit, we need to estimate the phase angle between I and V1. According to the AC circuit, the voltages V1 and V2 both are having same polarities. That's why the resultant voltage we can take it from the phasor diagram. That is, by considering this as a reference, this V1 is having 45 degrees positive. We should move in counterclockwise direction, which is plus 45 degrees, and V2 minus 45 degrees. Then the resultant voltage, total voltage, which is having 200, this is V, at an angle 0. This magnitude, we can take it 200 at an angle 0. According to the circuit, this is 10 ohms resistor and inductor, both are connected in parallel. That's why the current I is, it is the vector sum of IR and IL. Both are connected in parallel. That's why I can take it I is equal to IR plus IL, where IR is V by R 10 at an angle 0 and V by L, this is 10 at an angle plus 90 degrees. This is 200 at an angle 0. Finally, we are getting the current. This is 200 at an angle 0 means 20 plus 20 at an angle minus 90 degrees. We are getting this one. The current lags the reference total voltage under phasor diagram. I can consider this as a minus 45 degrees. Then the phase angle between I1 and V1 is minus 90 degrees. A two-port network is described as, in terms of ABCD parameters, A equal to D equal to 3 by 2 is equal into B equal to 4 by 3 into C. We need to estimate the value of Z11. Whenever for a two-port network, if you want to find out a single element of any parameters, first we have to consider the condition for that particular element. Here we need to define that element. Once you take the Z11 impedance is, it is the ratio between voltage to current V by I The first subscript indicates the current, first subscript indicates the voltage, second subscript indicates the current because it is impedance. And these impedance parameters are also called open circuit parameters. Already we have taken I1, then we need to consider the I2 is equal to 0. Nothing but for this two-port network, we need to define the ratio of input voltage and input current when I2 is equal to 0. According to the ABCD parameters, you know that ABCD parameters we can define input port variables in terms of the output port variables. That is, for ABCD parameters, V1, I1 we can express in terms of A V2 minus B I2, C V2 minus D times of I2. By considering this condition to define the Z11 element, we have to take I2 is equal to 0. Under I2 is equal to 0, we can neglect these two. Then the ratio of V1 by I1 is equal to Z11, which is equal to A by C. From the relation, that is the network or two-port network is described in terms of these ABCD parameters. From this relation, I can get A by C value is equal to 4 by 3. This is impedance, that's why units are ohms. Right. In the given question, an electric bulb is consumed the energy of 13.28 kilojoules for 20 seconds. We need to estimate that what is the voltage across that. You know that the energy consumed by this bulb W is equal to here given as 13.28 kilojoules. Energy you can define, it is W is equal to what it is. Power we can define rate of energy dW by dt. Then W is equal to integration of pdt. Energy we can define in terms of power 13.28 K watts second. From this 13,280 watts second. From this we need to estimate the voltage. To define that voltage we need to take the total charge. To obtain the charge within the given time, using the current, I can estimate the charge Q equal to I into T. That is, the 4 amperes current is passing through the bulb with 20 seconds. Then 80 coulombs, we are having that charge. Using the 80 coulombs and energy, I can define W is equal to or potential difference, we can take it, or EMF. EMF means electromotive force, which is the work done to move a unit positive charge from one point to other point is called electromotive force, which is nothing but voltage. Now we are having the energy and charge for that. From this I can estimate the total voltage across that bulb, which we are getting 166 volts. Right. From this, we need to estimate for a coil. The applied current is variation is given from 0 to 7 seconds. We need to estimate how much the energy stored by the inductor up to t equal to 6 seconds. Now, at t equal to 6 seconds, the current passing through the inductor is equal to 5 amperes. Using that directly, we can take it the energy stored by the inductor. We are having the relation of energy in terms of current of Li square, that is 1 by 2 times of L value is 4 henries and I square is, we are getting 50 joules. And here we need to see that it was given that up to t equal to 6 seconds, up to t equal to 6 seconds, once you consider that the value of current, it is a constant from 5 to up to t equal to 7. That's why we can use the formula WL is equal to half Li square. For this question, we need to estimate the how much power dissipated by the resistor R equal to 1 ohm. The applied voltage across the resistor R equal to is given. We are having an equation for any function f of t, which is a0 plus a1 cos omega 1t plus a2 cos omega 2t plus so on, b1 sin omega 1t plus b2 sin omega 2t plus so on. If this function, if you consider the RMS value, we can take it f of RMS is equal to under root a0 square plus 1 by 2 times of a1 square plus a2 square plus so on b1 square plus b2 square. This is the function RMS value. Here also, whenever given any voltage function, the circuit values are always RMS values. To define the RMS value for this applied voltage, we need to take this formula. Before going to this take formula, we have to see that all the trigonometrical functions are having operating frequencies are. Here operating frequency is 200 radians per second, here 100 radians per second. Again we are getting this cosine term 200 radians per second. That's why we need to consider this one. Both are operating at the same operating frequency. We should consider the effect of this signal 6 sin 200t and minus 10 cos 200t minus 45 degrees. For that, once you consider this one, this I can write minus 10 cos A cos B plus sin A sin B cos A minus B, that is cos A cos B cos 45 is 1 by root 2 plus sin A sin B sin 200t into 1 by 2. The resultant voltage we are getting Vs value 6 sin 200t, here we are having 10 by root 2, 6 minus 10 by root 2 into sin 200t. This is the first term for 200 radians per second, and minus 10 by root 2 cos 200t. This is the cosine term, and one more sine term we are having with 100 radians per second. Now with that we can take it the resultant applied voltage Vs is equal to 1 by 2 times of, this is 1 by 2 times of 6 minus 10 by root 2 whole square minus 10 by root 2 whole square plus 8 square. Once you get this RMS value, I can take it the total power dissipated by 1 ohm resistor is equal to Vs of RMS whole square by 1 ohm. This value we are getting according to the given 57.57 watts. For this example, you need to remember that whenever the two signals which are having the same operating frequency, we need to estimate the resultant magnitude of that operating frequency signal. For this circuit, we have to estimate the current in figure A by using the data in figure, current in figure B by using the data in figure A. Once you identify in figure B, which is exciting only with one source. Network is defined linear network, and it is also given this network should be resistive network. That is also important. Once you consider this total network is resistive network, if it is excited with single voltage source or current source, if you want to get a single branch response, we need to take that across the required branch, the entire network we need to replace either Thevenin's or Norton's according to the given data. Let us see this. The figure A, which is having a open circuit voltage with the input is excited with 5 amperes. But here the output is excited with 8 amperes. We need to estimate the open circuit voltage. According to figure A, I can estimate this entire network as a Thevenin's equivalent. For Thevenin's equivalent, if the excitation is 8 amperes, how much the open circuit voltage? From figure A, when excitation from the input side is 5 amperes, we are getting output side voltage as 8 volts. Here I would like to consider the reciprocity theorem as well as homogeneity principle. By using the reciprocity theorem, if you interchange the excitation and response, the ratio is constant. I would like to consider this 5 ampere source here, and you will get the open circuit voltage here 8 volts. But I need for 8 ampere source. Then we have to use the homogeneity principle. Then the circuit will be like this. By considering the 8 ampere source, excitation, and what is the open circuit voltage? This VOC we have to estimate. This is a linear network which is having only passive elements. Then from the figure A, I can take it from figure A by RPT, reciprocity theorem and homogeneity principle. Homogeneity principle, I can say that for 5 amperes, we are having open circuit voltage is 8 volts. For 8 amperes, what is the open circuit voltage? This VOC we need to estimate. VOC is equal to 8 into 8 by 5, nothing but 64 by 5 volts. Once you get the VOC, To convert this entire network as a Thevenin's equivalent, that is a single voltage source with series resistance across the load circuit, 1 ohm resistor. This VOC we got 64 by 5 volts. We need to estimate the R Thevenins. To get the R Thevenins across 1 ohm resistor, we have to take the help figure A. From the figure A, whenever if we take that R Thevenins, where we need to find out the R Thevenins between these two terminals. If you want to get the R Thevenins between these two terminals, we need to replace the all sources by their ideal conditions at internal resistance by their ideal conditions, nothing but if it is voltage source given short circuit, current source given open circuit. Here current source. For current source we should consider this is open circuit. From the figure A, I am able to get it that R Thevenin's value because we don't know the resistor values and resistor positions. That's why we don't know the passive network. For that, we have to estimate the applied voltage and resultant current. That ratio gives R Thevenins. Now I can say that R Thevenins across this, which is equal to 10 volts by 5, 2 amperes, 2 ohms resistor. Once you consider the R Thevenins here, 2 ohms resistor, I can estimate the current passing through this, which is total voltage by total resistance 64 by 5 by 2 plus 1. We are getting 64 by 15 amperes. For this example, we need to estimate the d square V of t by dt square at t equal to 0 plus. To obtain the value of this d square V of t by dt square, first we are able to estimate the V of t, which is voltage across capacitor. This is V of t. We have to consider that. According to the switching action, before t equal to 0, switch is opened. That's why the capacitor is not affecting with the source. There is no initial charge for the capacitor. After t equal to 0, switch position is closed. Then capacitor is affecting with the source. Nothing but this capacitor voltage is charging voltage. To obtain a charging voltage, the voltage equation we are having that V is equal to, or Vc of t is equal to V into 1 minus e power minus t by tau. This V is steady state voltage of the capacitor. To obtain the steady state voltage of the capacitor, under steady state, capacitor act as open circuit. We have to estimate voltage across this one, that is open circuit voltage. Once you consider under steady state, after t equal to 0, switch is closed, current passing through this one is equal to I. With that, I can take it. The voltage across capacitor under steady state, I can take it I into R. With that, the voltage equation for capacitor after t equal to 0, this equation is valid for t greater than or equal to 0. Once you obtain the voltage equation for capacitor after t equal to 0, I need to consider that dV by dt, that is differentiate with respect to t. Once you differentiate this, here we are getting IR, differentiation is 0, e power minus t by tau, where tau is time constant, minus t by tau and into 1 by RC, because e power at is e power at into a. With this RR will be cancelled. Here we are getting this value I by C into e power minus t by RC. We need d square v of t by dt square. Once again you have to differentiate this. By differentiating this, I by C into e power minus t by RC into minus 1 by RC. At t equal to 0 plus d square Vc of 0 plus by dt square, we are getting t equal to 0, e power 0 is equal to 1, with that minus I by RC square, volts per ampere square, volts per second square, volts per second square. But in this example, two networks are connected in series. Since the current in the input port current in the first network is same as the input port current of the second network. That's why these two networks are connected in series. We need to estimate the value of here V2 by Vs. First, we have to estimate the resultant Z parameters. In series connection, we can add the Z parameters. For the network 1, Z parameters already given. For network 2, we need to estimate the Z parameters. This is shunt element. For shunt element, Z parameters, we are having Z, Z, Z and Z. If it is series element, for series element, we cannot define the Z parameters. Now, once you get the Z parameters of this one, then the total network Z parameters you will get it. Z is equal to Z1 plus Z2. Here, these are the Z2 values which I can take it 10, 10, 10. This is Z2 for network 2. Total network Z parameters I can take it here 12, 8, 8 and 20. And shunt element Z parameters 10, 10. Once you take the entire network Z parameters matrix, you will get it here 22, 18, 18 and 30. Now I can express the voltages equations in terms of currents. V1 is equal to 22I1 plus 18I2 and 18I1 plus 30I2. Our required value is V2 by Vs. To obtain the V2 by Vs value, first I can define the Vs in terms of V1 or V1 in terms of Vs. From the network, I can take it V1 is equal to Vs minus 5 times of I1. By considering the V1 here, Vs minus 5 times of I1 is equal to 22I1 plus 18I2. From this Vs I can define 27I1 plus 18I2. Now V2 also we can take it in terms of I2, that is load current is equal to minus I2. V2 I can take it minus 20 times of I2. Now from the second equation, I can take it. I2 value is V2 by here. V2 is equal to 18 times of I1 plus 30 times of I2. I2 value is equal to, we are having minus V2 by 20. And I1 also we can express in terms of V1 or Vs. By using these two equations, I can get the V2 relation. Vs is equal to, finally, 27 times of V2 by 5 V2 by 36 plus 18 times of minus V2 by 20. From this, V2 by Vs is equal to 0.3508. From these two equations, first one, and this is the second one. With these two equations, from 1 and 2, we will get the ratio between V2 and Vs as 0.3508. For this coupled circuit, we need to estimate the coefficient of coupling. To obtain the coefficient of coupling, you need to know the mutual inductance and two self-inductances. From the given circuit, self-inductance for L2 is given, and we need to estimate the mutual inductance and self-inductance of the first coil. For that, it was provided the L equivalent between 1 and 1 dash terminals when the 2 and 2 dash are open circuit, first case, and second case is short circuit. According to the first case, whenever these two are open circuit, we can say that the L equivalent is equal to L1, since there is no secondary winding current. If there is no secondary winding current or coil to current, we will not get any mutual inductance, because mutual inductance in the first coil is due to one second coil current. That's why the L equivalent whenever this is open circuit is equal to L1, I can take it. Here that value I have taken L1 is equal to 8 henries. Second condition given, that is when 2 and 2 dash are short circuit, the L equivalent value is given 5 henries. Whenever if you provide short circuit, there is a secondary winding current, nothing but coil 2 current. Then mutual inductance will coming into the picture. To obtain the mutual inductance value, we need to take the equivalent circuit of this coupled circuit. The equivalent circuit of this coupled circuit is this one. Whenever the two dots at that particular coils are entering, L1 minus M, L2 minus M and M. L2 given as 4 henries. That's why I have taken 4. Once you provide these 2 and 2 dash as short circuit, I can say that L equivalent is equal to L1 minus M square by L2. From this, I can say the L equivalent is equal to L1 minus M square by L2 as 5 henries according to the given. Now L1, you know that 8 and M square by 4, which is equal to 5. From this you will get M value is equal to under root 12, which is 2 root 3. From this I can define the K value, which is our required value, coefficient of coupling. 2 root 3 by under root L1, which is 8 into 4. You will get 0.612. It is the K value. Right. For this circuit, we need to estimate the dynamic impedance. This is a tank circuit, which is under RLC, parallel resonance circuit. For this, he was given operating frequency and bandwidth. Using this, we have to estimate the dynamic impedance. The dynamic impedance, which we will get it under resonance condition. Under resonance condition, by considering that total impedance or admittance, By providing that imaginary part is equal to 0, you will get the real part only. That real part here we are considering as a dynamic impedance. To obtain the dynamic impedance of this tank circuit, we are having the formula L by RC ohms. For this L by RC ohms, we need to estimate the L value and C value. To get the L value and C value, since R value is given, he was given that bandwidth. From the bandwidth of this R by 2 pi L, I can estimate the L value because the bandwidth is, we are considering R by 2 pi L, that is 20K given. From this L value we are getting L is equal to 39.79 microhenries, and to obtain the C value we are considering the operating frequency. For the dynamic impedance, we are considering the operating frequency as a resonant frequency. The resonant frequency for the tank circuit, we are having 1 by 2 pi under root 1 by LC minus R by L whole square. Once you take this formula here, R value 5 ohms, L value 39.79 microhenries, and F naught is 500 kilohertz is given. From this, you will get the C value. C is equal to 2.54 nanofarads. By getting that L, R and C, I can take dynamic impedance is equal to L by RC. That is, L is 39.79 microhenries, 10 power minus 6 by R is 3 kilo ohms. Right, for this AC excitation, this is the combination of R, L, C. As per the given circuit, R and C are connected in parallel, and total combination inductor is connected in series. Here, he was given the values of VAB and VBC magnitudes, which are VAB is equal to VBC is equal to 100 volts given. This is the magnitude. And the vector sum of, whenever AC voltage, we need to consider that vector sum of VAB and VBC as a 100 volts. I would like to consider that the vector sum is V, total voltage as Vs, this is Vs. It is vector sum of VAB and VBC. To obtain that value of the angle between VAB and VBC, I need to take that Vs is equal to under root VAB magnitude whole square plus VBC magnitude whole square plus 2 VAB and VBC cos alpha. From this, you will get 100 is equal to under root 100 square plus 100 square plus 2 into 100 into 100 cos alpha. From this, alpha value you will get it 120 degrees. Once you get the alpha value is equal to 120 degrees, now I can take the vector diagram for VAB and VBC. These two vectors are displaced from each other is equal to 120 degrees. The resultant voltage is, this is Vs. And this angle is equal to 120 degrees. Total angle is 120 degrees. Angle between VAB and VBC. Now here, the current passing through the total circuit is given, which is existing in the inductor, same current, IL is equal to 5 amperes. Once you see this, the voltage across inductor is equal to VBC. You know that across pure inductor, the voltage and current displaced from each other is equal to 90 degrees. That is, current lags voltage by an angle 90 degrees. Now I can take that here, VBC, IL is having 90 degrees phase shift with respect to VBC. Once you take that IL with respect to VBC is 90 degrees, then I can say that the angle between VAB and IL is 30 degrees. And by considering this circuit, VAB across R and C, with that, I can estimate the current vector in the resistor. From the phasor diagram, I can develop the IR and IC because the vector sum of IR and IC, IC is equal to IL. That's why here the IL is, it is the vector combination of IR and IC, this one. Using this, I can take it IR vector value. This is a right angle triangle. We know hypotenuse, that is 5 amperes, and we know that angle. This is the adjacent side. Adjacent side value we need to consider as cosine. That's why IR is equal to IL times of cos 30 degrees. By considering that, IR value will get 5 cos 30 degrees. 5 by 2 times of root 3. Once you will get IR, we are having VR, that is VAB magnitude. Then R is equal to VR by IR. The magnitude VR is equal to VAB by IR. 100 by 5 root 3 by 2. From this, you will get the R value is equal to 23.09 ohms. Right. For this circuit, we need to estimate the I of t after t equal to 0. For t greater than or equal to 0, we need to estimate I of t. According to the given circuit, switching action is provided and energy storage elements are present. Before going to that, after t equal to 0, first we have to see that whether the energy storage elements are having initial values or not. For that, take the switching action before t equal to 0. Before t equal to 0, the switch position is at A. When the switch position at A, only inductor is affecting with the 20 volt source. Capacitor is not affecting. That's why the initial voltage of capacitor is equal to 0. To obtain the initial current of inductor, we need to consider at t equal to 0 minus. At t equal to 0 minus, inductor act as a short circuit. For DC, inductor act as short circuit. The short circuit path current we can estimate, which is 20 by 10, 2 amperes. Now, inductor is having initial current. Capacitor initial voltage is equal to 0. We have to take that after t equal to 0. After t equal to 0, switch position at B. Once you see that the LC network, which is not having any source, which is source free circuit, for this inductor is acting as a source. With that, the current value how to estimate. Once you take that circuit after t equal to 0, for t greater than 0, here capacitor as it is capacitance and inductance in parallel with current source, initial value we are having. This is 2 amperes. We got that initial value from this circuit, IL of 0 minus, where IL of 0 minus is equal to 2, which is equal to 20 by 10, 2 amperes, which is IL of 0 plus I naught. Now this is 1 henries. This is after t equal to 0. This is after t equal to 0, 100 microfarads. Now whenever LC circuit is there, better to consider in terms of S domain. For t greater than or equal to 0, by considering the LC circuit, here I can take it inductance as Ls, current source constant A by S, this is S, and capacitor 1 by Cs. 1 by Cs you will get 10 power 4 by S. This is ohms, this is ohms. And we need to estimate the current passing through this combination, I of S. Here we need to use the source transformation technique. By STT, I can get the LC circuit like this, a voltage source in series with the same inductance. This is S, this is 10 power 4 by S ohms. As per the current convention, this is negative, this is positive, and the voltage source value is equal to S into 2 by S, which is equal to 2 volts. According to the given current direction, and this is I of S, and the voltage source polarities both are same, that's why I can take it, the I of S value is equal to applied voltage here 2, this voltage source value by total resistance S plus 10 power 4 by S. With this you can take it 2S by S square plus 10 power 4. To get the value of I of t, which is current passing through the inductor, we need to take the inverse Laplace transformation. By ILT, you will get it, I of t is equal to 2 into, this is S by S square plus A square, which is cos AT. Now 2 times of cos 100t amperes, which is valid for t greater than 0.